All right, let's dive in. We're going small this time, super small, to the nanoscale, actually. That's where these tiny particles called quantum dots are, and they're making a big splash in all kinds of fields.
They really are amazing, these little quantum dots. They're like, well, imagine microscopic chameleons that change color depending on their size. And the things they can do, displays, solar panels, you name it.
Okay, back up for a sec. You got to paint a picture for our listeners. Think about it. Paper-thin TVs, super efficient solar panels, even sensors that can pick up on the tiniest changes in your body. That's the promise of quantum dots, or QDs, as the cool kids call them.
QDs are basically these teeny, tiny crystals, so small they're made of just a few hundred or thousand atoms. We're talking nanometers here, a billionth of a meter.
Hold on, let me grab my nano ruler. Just kidding. But seriously, that's tiny. What makes something that small so special?
It's all about quantum confinement. Basically, electrons in regular materials can move around pretty freely, but in a QD, they're squeezed into this super tiny space.
Like being stuck in a packed elevator.
You're right.
Right. Except way smaller.
Exactly. All those electrons crammed in there cause these really cool quantum effects to happen. And the thing is that the electrons can only exist at very specific energy levels. It's kind of like a ladder. They can only be on the rungs, not in between.
So tighter squeeze, more packed energy levels. I'm following so far.
And that's where things get interesting. See, when a QD absorbs light, it gets excited, jumps up to a higher energy level, but it can't stay there forever. Eventually, it's got to release that energy, and when it does, it emits light as it drops back down to a lower level.
So it's like a tiny light converting machine, absorbs one color, emits another.
You got it. And the color it emits, that depends on the energy difference between those levels. And guess what determines that difference?
The size of the dot.
Bingo. Want blue light? Make a small dot. Want red? Make it bigger. It's like tuning a musical instrument.
Okay, I'm seeing how this works. And speaking of cool stuff, we've got this brand new review paper on QDs. Straight from some brilliant minds at MIT. It covers the latest advancements, all the potential applications of these little guys.
This paper, oh man, it's like a peek into the future. It shows just how far we've come with QD research and the possibilities. They're pretty mind-blowing.
Yeah, this paper is jam-packed.
Yeah.
Displays, solar energy, bioimaging, even quantum information technology. Crazy. But let's not get ahead of ourselves. First things first. How do we actually make these tiny magical dots?
Good question. The paper talks about two main approaches, top-down and bottom-up. Imagine you're building a tiny house. Top-down is like starting with a big block of wood and carving away until you get the shape you want.
Okay, I get that. Sculpting, basically. What about bottom-up?
Bottom-up is more like building with Legos. You start with individual atoms or molecules and assemble them piece by piece into the structure you need.
So it's like growing a crystal, carefully controlling how those atoms arrange themselves.
Right. And both ways have their pros and cons. Top-down can be super precise, but it's expensive and time-consuming, especially at this tiny scale. Bottom-up, more cost-effective, can be scaled up easier, but it can be trickier to control exactly.
So precision versus practicality. Got it?
Yeah. And the best method really depends on what you're trying to do with the QDs. Big applications like displays and solar cells, bottom-up makes more sense. But for specialized stuff like quantum information tech, where precision is key, top-down might be the way to go.
Makes sense. It's all about picking the right tool for the job, right?
Mm-hmm.
Now, of all the things we can do with these QDs, the one that really catches my eye is their potential in displays. Imagine a TV with even more vibrant colors that also uses less energy.
Oh, yeah. And the paper gets into the nitty-gritty of how QDs are making that happen. Remember how we talked about how they emit different colors depending on their size? Well, in a display, they can act like the backlight source, converting blue LED light into a whole spectrum of colors with incredible precision.
It's like having a tiny artist palette inside each pixel, mixing all these colors together to create a huge range of shades.
Exactly. And because they're so efficient at emitting light, they don't waste as much energy as heat, so you get lower power consumption compared to your regular LCD or OLED screens.
Best of both worlds. Better colors and lower energy bill. Sign me up.
The paper even talks about this specific QD LED design called the inverted structure. It helps with some of the challenges with making them efficient and making them last longer.
Hold on, break that down for me. What's so special about this inverted thing?
So in your typical QD LED, you've got all these layers of material, the electrons and holes, those things that carry charge and make the light happen. They have to move through all those layers. Imagine driving through a city with tons of traffic lights and one-way streets. Not very efficient, right?
So those poor electrons and holes are stuck in rush hour traffic, wasting time and energy.
Pretty much. But this inverted structure, it rearranges the layers to create a smoother path. It's like building a superhighway for those electrons and holes to zip through.
Now that's thinking outside the box, or inside the display, I guess.
Hmm.
So QDs and displays, it seems like a win-win. Better colors, more efficient, potentially cheaper. What's the catch?
Well, there are still a few hurdles to clear. One biggie is making sure all the QDs are the same size and composition. Remember, the color depends on the size, so if you've got a bunch of different sizes, you'll get a display with uneven color.
Yeah, because even a tiny size difference can throw the color off. Makes sense.
Exactly. And then there's the challenge of keeping those QDs stable over time. They can degrade, which obviously affects their performance and how long the display lasts. Like a beautiful painting that starts to fade, not good.
So it's about keeping those colors vibrant over time. Definitely something researchers need to tackle.
Absolutely. They're working on making those QDs more robust, trying new materials, coatings, and ways to protect them from degrading. It's a work in progress.
It sounds like there's a ton of cool research happening with QD-based displays. I can almost picture these little guys lighting up our screens in the future. It's pretty amazing to think about. But let's switch gears for a minute and talk about another fascinating area where QDs are making an impact. Solar energy. I'm curious, how can these tiny dots help us harness more of the sun's power?
That's where QDs really shine, and the paper gets into all the details. You see, traditional solar cells, they're kind of picky eaters when it comes to sunlight. They only absorb certain wavelengths and leave the rest behind.
Oh, came out, eat your photons. That seems like a waste.
I know, right? But QDs, with their adjustable energy levels, they can be designed to gobble up a much wider range of wavelengths. They're like the champion eaters of the solar world.
Now that's what I call a solar power upgrade. And speaking of upgrades, the paper mentions QDs can even help break through the Shockley-Queisser limit. Remind me what that is again, and how can QDs help us beat it?
Right, the Shockley-Queisser limit, think of it as a fundamental speed limit for traditional silicon solar cells. It's based on the properties of silicon, and it basically says you can only convert a maximum of about 33% of sunlight into electricity.
So no matter how hard we try, we can't squeeze out more energy from a traditional silicon solar cell. That's a bummer.
It is. But QDs, they can change the game. They can be designed to absorb a wider range of light, including those wavelengths that silicon just can't handle. This means we can harvest more of the sun's energy and potentially get way higher efficiencies.
It's like giving those solar cells a turbo boost. But just like with displays, I'm guessing there are some challenges to overcome before we see QD-enhanced solar cells everywhere.
Of course. Long-term stability is a big one. QDs can be sensitive to things like moisture, oxygen, and heat, and that can mess with their performance over time. Imagine those tiny QDs out there battling the elements day after day. It's a tough job.
So it's all about making those QDs tough enough to handle the real world.
Exactly. And then there's the scalability issue. We'd need to be able to produce these QD-enhanced solar cells on a massive scale to meet the world's energy needs. It's one thing to make a prototype in a lab, but it's a whole other ballgame to manufacture millions of them at a price that can compete with those good old silicon solar cells.
Yeah, it's like the difference between baking a cake for your family and trying to supply a whole city with cakes. Not quite the same thing.
Exactly. But researchers are working hard on both fronts. They're developing tougher, more stable QDs and figuring out how to manufacture them more efficiently. It's an exciting time to be watching this field evolve.
It definitely feels like we're on the verge of a solar energy revolution. And these little QDs are leading the charge. Now, before we move on, I want to touch on another area where QDs are making a splash: bioimaging. The idea of peering into the microscopic world of cells and molecules, it's just fascinating.
It is pretty mind-blowing. Imagine being able to tag specific proteins or cells with these tiny glowing beacons so we can track their movement and how they interact in real time. It's like watching the symphony of life unfold right before your eyes.
Okay, I'm hooked. But what makes QDs so good at this? Are there other ways to do this already?
Oh, they've got some serious advantages over other methods. First off, their brightness. QDs are like tiny spotlights, super easy to detect, even if there aren't many of them. It's like trying to spot a firefly in the dark. The brighter it is, the easier it is to find. Right?
So they're like the superstars of microscopy, shining bright even in a crowded cellular landscape.
Exactly. And because they emit light in a very specific color range, it's easier to target them and reduce background noise, like a laser focus on exactly what you want to see.
So no distractions, just a clear view of the action.
Precisely. And unlike some other fluorescent probes that fade quickly under the microscope's light, QDs are incredibly photostable. They can handle those long imaging sessions without any problems.
So they're not afraid of the spotlight. They're ready for their close-up.
Exactly. And the paper highlight all sorts of cool ways we can use them. For instance, tracking how drugs move within cells so we can study how to deliver them more effectively. Imagine following a drug molecule on its journey, seeing exactly how it navigates that complex cellular world.
It's like having tiny GPS trackers attached to those drug molecules, guiding them to their target.
Exactly. And in cancer research, they're being used to tag and track tumor cells, giving us insights into how tumors grow and spread. By attaching QDs to those cancer cells, researchers can watch them, see where they go, and figure out how to stop them.
That's incredible. We're talking about potentially saving lives here, understanding and fighting diseases at the cellular level.
It really is groundbreaking stuff, and it's not just about tracking cells either. We can use QDs to image specific proteins and other biomolecules, getting a closer look at how they function.
So it's like having a molecular magnifying glass zooming in on the intricate machinery of life.
A perfect way to put it. And as we get better at making and attaching QDs, the possibilities just keep expanding. We can tailor them for specific tasks, adding coatings to target specific cells or tissues.
It's like having a toolkit full of specialized instruments, each one designed to unlock a different secret of the cellular world.
Exactly. And it's not just about seeing things. We can design QD probes to react to changes in their environment, things like pH, temperature, or even the presence of specific molecules.
So they're like tiny reporters, sending us live updates on what's happening inside the cell, giving us clues about how cells work and how diseases develop.
Right. And as nanotechnology, biotechnology, and imaging all come together, we can expect even more breakthroughs in QD-based bioimaging in the years to come.
This is really exciting stuff. It's amazing to see how these tiny dots are revealing the complexities of life. But before we move on to the next part of our deep dive, I got to ask about another aspect of QDs that has me totally intrigued. Their potential in quantum information technology. I know this is getting into some pretty mind-bending territory, but can you give us a crash course?
Sure. Quantum information technology basically uses the weirdness of quantum mechanics to process and transmit information in ways that are totally impossible with our regular computers. It's like opening a door to a whole new world of possibilities, going beyond the limits of what we know.
So we're talking about breaking the rules of computing as we know it.
Exactly. At the heart of a quantum computer is the qubit. It's like the bit in a classical computer, but way cooler. While a bit can only be a 0 or 1, a qubit can be both at the same time. It's called superposition.
Wait, hold on. Both at the same time? That doesn't make any sense.
I know, it's wild. It's like flipping a coin and having it land on both heads and tails at the same time. And this weirdness is what gives quantum computers their power. They can explore tons of possibilities all at once, solving certain problems way faster than any classical computer.
So we could crack codes that would normally take billions of years, maybe even unlock the secrets of the universe.
Exactly. And guess what? We can use QDs to create these qubits. For example, the spin of an electron trapped in a QD can act as a qubit.
Spin, like a planet spinning.
Kind of. Spin is a property of electrons, like a tiny magnet. And we can manipulate that spin to control the qubit, essentially writing and processing quantum information.
So we're using these tiny quantum dots to build the foundation of a whole new kind of computer. It's mind-blowing.
It is, but actually building a practical quantum computer is incredibly difficult. One big challenge is keeping those qubits stable because they're super sensitive to their environment. Like trying to balance a spinning top on a shaky table, the slightest bump can throw everything off.
So we need to create a safe haven for these qubits, protect them from any disturbances.
Exactly, and QDs are actually pretty good at that. They're easy to isolate, which helps protect them from noise and decoherence. It's like building a tiny fortress around each qubit.
Tiny fortresses for tiny particles doing big things. I love it.
Now, it's important to remember that quantum computing is still in its early stages. Building a large-scale, reliable quantum computer will probably take decades.
So it's a marathon, not a sprint.
Exactly. But the payoff, it could be huge. Think about revolutionizing medicine, materials science, artificial intelligence, cryptography. The potential is almost limitless.
It sounds as we're on the edge of a whole new technological era, powered by quantum mechanics, and QDs are right there in the thick of it. It's been an amazing journey so far, exploring the world of quantum dots, from those tiny crystals to their potential to transform entire industries.
We've covered a lot of ground. From making our screens brighter and our energy cleaner to unraveling the secrets of life and pushing the limits of computing, these little QDs are shaping the future.
And who knows what other wonders are waiting to be discovered as we delve deeper into the mysteries of these tiny, powerful particles.
It's truly a testament to human ingenuity and the constant push to discover what's possible.
Well said. And to our listeners, stay curious, keep exploring, and never stop being amazed by the world of science and technology.
Because that pursuit of knowledge is what drives us forward and helps us build a better world.
Absolutely. Until next time, keep those brains buzzing and those imaginations soaring. Welcome back to our deep dive into the amazing world of quantum dots. Last time, we got a handle on what these tiny particles are all about and saw how they could revolutionize things like displays, solar energy, even bioimaging and quantum information technology. But there's so much more to explore.
Oh yeah, we're just getting started. There are tons of areas where QDs could make a huge difference. It's like opening a treasure chest of scientific possibilities.
So where do we head next on our QD adventure? What other frontiers are these tiny particles illuminating?
Let's go back to solar energy for a bit. Remember that pesky Shockley-Queisser limit?
Yeah.
That theoretical cap on how efficient traditional silicon solar cells can be?
Yeah, it's like a speed limit for solar cells, holding them back from their true potential.
Exactly. Well, QDs can actually help us get around that limit.
Yeah.
The paper talks about some really cool ways to use them in solar cells to boost efficiency. One approach is to use QDs in something called a down-converting layer.
Down-converting layer. Sounds kind of mysterious. What's going on there?
Okay, so picture sunlight hitting a solar panel. Some of those photons have way more energy than the solar cell can actually use. It's like they're too powerful for the solar cell to handle.
So those supercharged photons are just going to waste.
Pretty much. That's where the down-converting layer comes in. The QDs in that layer act like energy converters, absorbing those high-energy photons and spitting them out as lower-energy photons that the solar cell can actually use.
So it's like they're taming those wild photons, bringing their energy down to a level the solar cell can handle.
Exactly. It's all about getting the most out of every photon, maximizing the efficiency of the whole solar cell.
Pretty clever. So the QDs are like energy matchmakers, making sure the photons in the solar cell are a perfect match.
Exactly. Now, another cool approach is to actually use the QDs themselves as the light-absorbing material in the solar cell.
So instead of silicon, we'd be using QDs to capture the sunlight. That's a pretty bold move.
It is, and it's showing some serious promise. QDs can be incorporated into all sorts of solar cell designs, including those based on perovskites, which are these new, super efficient materials that are starting to make waves.
Perovskites. Yeah, we talked about those earlier. They've got a ton of potential, but they can be a bit finicky, right?
That's one way to put it. They're super efficient, but not always the most stable. But when you combine them with QDs, it could be a real game changer, both in terms of efficiency and how long they last.
It's like the dream team of solar materials, each one compensating for the other's weaknesses.
I like that. But like with any new technology, there are still challenges to overcome before QD-enhanced solar cells take over the world. One of the big ones is figuring out how to make them last in the real world. Out there in the elements, QDs can be sensitive to things like moisture, oxygen, and heat, which can degrade their performance over time.
Yeah, it's a rough world out there for a tiny particle. They need to be able to withstand the heat, the rain, the constant exposure to the sun.
For sure. And then there's the issue of scale. We'd need to be able to produce these QD-enhanced solar cells on a massive scale to meet the world's energy demands. Making a few in a lab is one thing, but churning out millions of them at a competitive price, that's a whole other challenge.
It's like the difference between baking a batch of cookies for yourself and trying to keep an entire bakery stocked with cookies. The scale is just completely different.
Exactly. But researchers are making progress on both fronts, developing more resilient QDs and exploring new manufacturing techniques to make them more affordable. It's a really dynamic field to watch.
It sounds like we're on the cusp of a solar energy revolution, with QDs leading the charge. Now, let's switch gears again and dive into another captivating area: bioimaging. It's always blown my mind that we can actually see into the microscopic world of cells and molecules.
It's pretty amazing, isn't it? Imagine being able to attach these tiny glowing beacons to specific proteins or cells and watch them in action. It's like having a front row seat to the most intricate dance in the universe.
It sounds like a cellular ballet, with QDs as the spotlight. But what makes them so good for this? There must be other ways to do this, right?
Oh, yeah. But QDs have some serious advantages. First of all, they're incredibly bright. Super easy to spot, even when there aren't many of them. Like trying to find a firefly on a dark night, the brighter it is, the easier it is to see.
So they're like the stars of the microscopy world, outshining everything else with their brilliance.
Exactly. And because they emit light in a very specific color range, they're really easy to target, and there's very little background noise. It's like having a laser focus on exactly what you want to see.
No distractions, just a crystal clear view of the cellular stage.
Right. And unlike some organic dyes that fade quickly under the microscope's light, QDs are super stable. They can handle those long imaging sessions without any problems.
So they're not afraid of the spotlight. Bring on the close-up.
Exactly. And the paper talks about all sorts of cool applications for this. For example, we can use QDs to track how drugs move within cells. That helps us understand how to deliver drugs more effectively. Imagine being able to follow a drug molecule's journey through the cellular maze, seeing exactly how it gets where it needs to go.
It's like those tiny drug molecules have their own little GPS trackers guiding them to their destination.
Exactly. And in cancer research, QDs are being used to tag and track tumor cells. This gives us valuable insights into how tumors grow and spread. By attaching QDs to cancer cells, researchers can literally watch them, see where they go, and try to figure out how to stop them.
So we're talking about potentially life-saving applications here, fighting diseases at the cellular level. It's incredible.
It really is, and it goes beyond just tracking cells. We can use QDs to image specific proteins and other biomolecules, giving us a glimpse into their roles in all sorts of biological processes. It's like having a molecular magnifying glass, allowing us to see the intricate machinery of life in action.
It's amazing to think that we can see these tiny components of life in such detail.
Right. And as we get better at making and attaching QDs, the possibilities are just going to keep growing. We can create QDs that are tailor-made for specific tasks with special coatings that target particular cells or tissues.
It's like having a whole toolbox full of specialized instruments, each one designed to unlock a different secret of the cellular world.
I love that analogy. And it's not just about visualizing things. We can design QD probes that react to changes in their environment, things like pH, temperature, or even the presence of specific molecules.
So they're not just passive observers, they're active participants, reporting back on what's happening in the cell, giving us valuable clues about how cells function and how diseases develop.
That's it exactly. And with all the advances in nanotechnology, biotechnology, and imaging techniques, we can expect even more breakthroughs in QD-based bioimaging in the future. Brighter QDs, more stable QDs, even more sophisticated QDs, all helping us probe the mysteries of life with incredible precision.
It's an exciting time to be following this field, seeing how these tiny particles are revealing the complexities of life.
Absolutely. And the applications go way beyond what we've talked about so far. QDs are also being explored for use in LEDs, lasers, sensors, and even, get this, quantum computing.
Quantum computing. That's something that always gets my brain buzzing. It's like the Wild West of computing, harnessing the weirdness of quantum mechanics to do things our current computers could only dream of. But before we venture into that mind-blowing territory, let's take a quick break. We'll be back soon to explore even more amazing applications of quantum dots, including their potential to completely change the way we think about computers. Stay tuned. Welcome back to our deep dive into the world of quantum dots. We've seen how these tiny particles are making waves in fields like displays, solar energy, and bioimaging. But now it's time to step into the quantum realm. That's right, we're talking quantum computing.
Quantum computing. It's where the familiar rules of classical physics kind of go out the window and we enter the mind-boggling world of quantum mechanics. It's a field that's full of challenges, but also huge potential, with the power to transform computing as we know it.
So where do quantum dots fit into all of this? What role do these tiny particles play in building these super powerful quantum computers?
Well, the heart of a quantum computer is the qubit. It's like the bit in a classical computer, but with a quantum twist. You see, a classical bit can only be a 0 or a 1, but a qubit can be in a superposition of both states at the same time.
Okay, now my head's spinning. Superposition. It's like these quantum particles can't decide what they want to be, so they're both 0 and 1 at the same time.
That's a pretty good way to think about it. And it's this weird superposition thing that gives quantum computers so much power. They can explore a bunch of possibilities simultaneously, solving certain problems exponentially faster than our regular computers.
So we're talking about cracking codes that would take classical computers billions of years to solve, maybe even figuring out the secrets of the universe.
Exactly. And here's the cool part. We can use QDs to create these qubits. For example, the spin of an electron trapped within a QD can be used as a qubit.
Spin, like a top spinning.
Kind of. Spin is a fundamental property of electrons. You can think of it like a tiny little magnet. By controlling that spin, we can control the state of the qubit, basically writing and processing quantum information.
So we're using the quantum properties of these tiny dots to create a whole new kind of computer. It's pretty mind-blowing when you think about it.
It is, but building a quantum computer that actually works is a huge challenge. One of the biggest hurdles is protecting those fragile quantum states of the qubits. They're very easily disrupted by their surroundings.
So we need to create like a safe space for these qubits to do their thing, shield them from all the noise and distractions of the outside world.
You got it. And QTs actually have an advantage here. They can be isolated from their environment pretty easily, which helps protect them from noise and decoherence, things that can mess with their quantum states. It's like building a tiny fortress around each qubit.
Tiny fortresses for tiny particles doing big things. I like that image.
Now, it's important to remember that we're still in the early days of quantum computing. Building a large-scale, reliable quantum computer is a huge undertaking. It'll probably take many years, maybe even decades, to get there.
So it's a long road ahead, but the destination is definitely worth the journey.
Absolutely. The potential payoff is enormous. Quantum computers could revolutionize fields like medicine, materials science, artificial intelligence, you name it. We could see breakthroughs that we can't even imagine right now.
It's like we're standing at the edge of a new technological frontier, and quantum dots are helping lead the way. It's been a truly incredible journey exploring the world of these tiny but powerful particles.
Yeah, from making our screens brighter and our energy cleaner to unlocking the secrets of life and pushing the boundaries of computing, QDs are shaping the future in some really amazing ways.
And as research continues, who knows what other amazing things we'll discover about these tiny particles.
It's inspiring to see the ingenuity and creativity of scientists pushing the boundaries of what's possible and creating a brighter future.
Well said. And to all our listeners out there, stay curious, keep exploring, and let's keep pushing the boundaries of what we know and what we can achieve.
That's what it's all about. That pursuit of knowledge is what drives us forward and helps us build a better world for everyone.
Couldn't agree more. Until next time, keep those brains buzzing and those imaginations soaring.